Okay, well, today we start our chapter on radicals, which are molecules with unpaired electrons, and it's super radical. And in the spirit of adjectives from the 80s, we're going to talk about plastic today. And it's going to be fantastic. There's songs about that associated with Barbie. It's fantastic. So what we're going to do is I'm going to show you some structures of various polymers. A lot of the things you can see and touch in the world around you are actually made of plastic. Recycling, you can see numbers on different types of plastics, and we're going to talk about what those mean and what different kinds of plastics are. We're going to see that a lot of them, not all of them, but a lot of them are made by a process that involves radicals. So I just want to show you a few structures of some polymers that are plastics. And in polymers, you want to know what the structure of the polymer is, and you want to know what the individual repeating subunit of that polymer is. Poly stands for many, and so a polymer is a chain of repeating subunits. So, for example, polyethylene, or abbreviated often as PE, is a polymer of the following subunit, individual subunit, which we will call a monomer, and that monomer is simply ethylene. So in polyethylene, you have a lot of these 2 carbon subunits. Are we recording? Yeah. You have these 2 carbon subunits that are linked together covalently in a chain. So I'm going to draw individual subunits. And then I'm going to draw in red the bonds between those individual subunits. Not intended to show you bond lengths. Those bond lengths are all single bonds. They're all supposed to be equal to each other. But that's the idea, is you make this polymer by linking several of these subunits together. And just to highlight the point, the subunits are added sequentially in a reaction individually to give you the full-length polymer and so on. All right, so that's polyethylene. Polyethylene actually comes in a couple of different varieties. What I've shown you here would be an example of low-density polyethylene, or LDPE. You probably heard that term before. Whoa, that eraser was erasing too much. There we go. This is found in a lot of containers and tubing and plastic bottles. Yes?
Is there a reason why the polymer doesn't have any double bonds in it?
Is there a reason the polymer doesn't have any double bonds in it? Yes. Am I going to answer that question right now? No, but I will soon. Okay. It turns out the double bonds are involved in the making of the reaction. I feel like such an old person. Look at me looking at you over my glasses. You know, next time I'm going to come with a little chain that links so I can just hang it. All right. So that's low. Oh, you know what? I was totally wrong. I'm sorry about that. What I've shown you here is not low-density polyethylene, but high-density polyethylene. So I take that back, HDPE. On your recycling code, if you look at a plastic and it's HDPE, you're going to see it with the code of 2. High-density polyethylene is relatively rigid. So it's found in a lot of places where you need a container that's not going to distort its shape. HDPE is found in a lot of toys, in signs. We're going to talk about the difference between high-density and low-density polyethylene. So now let me show you the structure of low-density polyethylene. I will go ahead and answer the question that I'm sure is on all of your minds. How much of this is going to be on the test, and what do I need to memorize? Let me just say that you know that I am perfectly capable of asking you what molecule smells like bananas. So prepare accordingly. You should make it look when you take the exam as though you were here today actually listening. Okay, got it? All right. So the low-density polyethylene is like high-density polyethylene, only low-density has branch points at which additional chains march on. So here is one such branch point with additional subunits of polyethylene, where the squiggly lines indicate sort of an indeterminate number of a number of subunits branching off in either direction. Because, I mean, I'm going to stop using color for the branch points because it gets a little bit excessive, but and the branch points are spaced sort of randomly. So I'm giving you one example of where the branch points might be, but that where the branch points occur in this polymer, I will show you where they come from. It's not really controlled. So you have to imagine low density polyethylene as just having branch points that at some point it becomes difficult to talk about this being the main chain and these being branches, because maybe these are now the main chain and this is a branch. In any case, in low density polyethylene, you have a large network of these carbon chains linked to each other. The length of the polymer, the location of the branch points, their proximity to each other is not necessarily controlled, though if you get into material science and engineering and some polymer chemistry, being able to control the location of the branch points, whether they're this far apart or this far apart, can be important. Let's talk about why the branching causes a difference in properties. Because the difference in properties is illustrated by these adjectives, high density versus low density. So now we're going to jump back in our brain to chapter 3 of this class, where we talked about intermolecular interactions. The closest analogy for high density, low density versus low density polyethylene is really what we saw in chapter 3 for fats versus oils, which was also a question on an exam, right? Who remembers the difference between a fat and an oil? What was it? Solid at room temperature is fat, liquid at room temperature is an oil. Okay, and why are the fats solid? No double bonds, right? No cis double bonds, right? Why are the molecules with cis double bonds liquid? You don't know, but you memorized it. Okay, we'll talk about it again. Maybe you know. So within the fat or the oil, I'm not going to show the whole structure of the triglycerides, just the carbon chain. For fats that are solid at room temperature, you have this long linear carbon chain. There are 3 of them in each triglyceride molecule. We're going to zoom in on one nonpolar chain on one triglyceride molecule and then another nonpolar chain on another triglyceride molecule. When there are no double bonds, the carbon chains are relatively flexible and they are free to adopt whatever conformation allows them to approach each other most closely. Okay? Now, why do we care whether they approach each other closely? What intermolecular interaction kicks in when molecules get really close together? Van der Waals, good, those dispersion interactions, which are directly related to how closely these carbon chains can approach each other. If instead of having the long carbon chain that is linear, the long without double bonds, the long saturated carbon chain, you have a carbon chain that has a couple or even just one double bond, there is no longer flexibility for rotation around those double bonds. In fact, at least in the immediate vicinity of the double bonds, there's some rigidity. That prevents the chains from approaching each other, from adopting conformations where they can approach each other real closely, right? whereas the carbon chains above, because they're so flexible, can adopt whatever conformation allows them to approach closely. The carbons with cis double bonds are oriented such that they can't. Does that make sense? Okay, so if the molecules with the cis double bonds can't approach each other closely, their van der Waals interactions are weaker, less is holding them together, they're liquids at room temperature instead of solids. A similar thing sort of happens with low density versus high density polyethylene. You will notice that for high density polyethylene, there are no branching points. So individual polymer chains are able to approach each other more closely. In contrast, when there's a lot of branching, the network of polymer molecules is somewhat inflexible and somewhat difficult for the individual polymer chains to approach each other closely. High density, because they can pack closely. Low density, because they can't pack as closely. This leads to stronger intermolecular forces here, weaker intermolecular forces here, which leads to some of the different properties of low versus high density polyethylene. Toys that are made out of high density polyethylene are relatively rigid, whereas a bottle made of low density polyethylene you can totally squeeze and distort from its shape. Yes?
Can you give an example of something we can see that would be made of high density versus low density?
Something that you could see or touch made of high density versus low density, let's see. Well, I don't know. Thanks to all the detergent companies putting together the Tide Pods and whatever, do most of us use that now, or do you still buy the big plastic bottle of detergent and pour it out into the cup? Some of you still do that? Yeah. That detergent bottle is usually high density polyethylene. Whereas low density polyethylene, what's a good example of that? Some, not all, but some plastic bottles. So there's another kind of polymer that is often used for plastic bottles, but if you look on the bottom of that, see if you can see the number 2, it might be there. What is it? You can't see the code, that's okay. Yeah, anyway, some flexible plastic bottles like that are going to be low density polyethylene. Okay. Other questions on that? Yeah.
Could you repeat what the 2 and 4 stand for?
What do the 2 and 4 stand for? That's the recycling symbol. That's just for sorting plastics. Yeah. So if you see a container and it has this symbol on it, you now know what the structure of the molecule is. If you see the number 4 on it, you now know what the structure of the molecule is. I don't think they're ranked in order of ease of recycling. I think those are just numbers. Okay, so some other polymers will share this basic structure of a 2-carbon subunit. Only we're going to play around with what's attached to some of the carbons of the alkene. So, for example, if you have a monomer that looks like this, 2 carbons of the alkene where this is a benzene ring, this individual monomer is called, it could be called phenylethylene, but nobody calls it that. They call it styrene. Some of you are like, oh, because you've heard the term before, polystyrene. So polystyrene has the same basic structure as polyethylene. The difference is that with polystyrene, what's the best way to do this? I'm going to abbreviate those benzene rings. On alternating carbons, you've got phenyl groups. So this polymer that I've drawn for you has 1, 2, 3, 4, 5, 6, 7, 8 different subunits of polystyrene. Of course, the actual polystyrene molecules that are used in plastics are going to have hundreds or thousands of those subunits. Okay, so polystyrene is often abbreviated as PS, and if you see the recycle symbol of 6, that's polystyrene. Common uses for polystyrene include polystyrene has some interesting properties and can be prepared in different ways. It can foam up, and so you can make polystyrene packing peanuts. Have you guys ever seen that? The world's kind of gotten better since I was a kid. It used to be you ordered something and you'd get this box filled with these little fluffy polystyrene bits to help insulate the material and protect it from mechanical damage. The problem is that then you would just throw them away and they would blow in the wind and then never degrade. So I think instead we don't necessarily do that so much anymore. Some plastic cutlery is polystyrene. So if you go to Taco Bell and you're eating your tostada or taco salad with a spork, I don't know if Taco Bell still uses sporks, deceptive spoons that poke you and cut your mouth, but are very versatile. I prefer the challenge. I prefer to use a spoon instead of a fork. In my office, I have this spoon I got from somewhere. I don't know where it was. Maybe it was Menchie's or somewhere, but it changes color when it's hot or cold, so it's really cool. But I use it in place of a fork. And noodles are really fun. I enjoy that challenge. Yeah, polystyrene is a little more brittle. The addition of those phenyl groups changes the way the polymers pack against each other, so polystyrene's a bit more brittle. Another fun thing you can do with polystyrene is the amount of space it takes up, the polymer takes up, depends greatly on how it was prepared. So you can get a sheet of polystyrene, transparent plastic, and you can color on it and make all kinds of interesting shapes and cut them out. When the polymer is prepared, it's heated up and then spread out and stretched. But if you heat it up again, you'll allow it to overcome the energy barrier between its current state and a much more compact state, and the interesting shape you've cut out will shrink. So some of you can look it up. It was, again, we're going back to the 80s when plastic was everything. Shrinky dinks. Have you ever heard of shrinky dinks? Yes. They're made of polystyrene. They're a shape, you prepare the polystyrene sheet in a way that's more spread out, but it's stable at room temperature. But if you heat it up, you allow the polymer chains to move relative to each other, and they sort of snap back to a much smaller shape. So look it up. You know, Amazon, you could probably have a shrinky dink pack to your house tomorrow to entertain you, or maybe Sunday. Yeah, go ahead.
Well, I was wondering, my buddy's water bottle has a 7 recycle symbol on it. What is that?
Okay, I don't know. Let's look it up. Let's see if it's in my notes. I don't know what it is, so 7, 7, 7. No, I haven't got any 7. So see if you can find it. Let's see. Recycle. Nope. Sorry, still looking it up. Anybody got an answer?
Other.
It means other. That's helpful. Yeah, sorry, I got nothing. So that means other. It's really helpful. But I do have the other symbols here, so. Oh, another example, somebody was asking earlier, I think it was Matt, what's an example of low-density polyethylene? The infamous plastic grocery bags. Yeah. So you can see massive differences in properties, right? You would never house laundry detergent in a plastic grocery bag, but it's fine for groceries. Also, sometimes these plastics have interesting properties, like if you've ever tried to tear a grocery bag, they rip in one direction, they stretch in another. I don't necessarily know why that is, but that has to do with the polymer structure. Let's do just a couple of more, maybe some ones that you've heard of. There are others that we won't get to. Let's see, we've done polystyrene. I'm going to erase the phenols. If our monomer is this, again, almost like ethylene, only we put a chloro there. That is called vinyl chloride, and the polymer is called polyvinyl chloride, or PVC. Okay. And that has chloros on every other carbon. PVC, let's see, I believe shows up. Three? Is that, you're just guessing? It is three. How did you know? You just know that, or you were just guessing? Well, you're right. You had a choice. Numbers 1 to 7. We've already done 3. So you've had about 50, 2 out of 3 odds. Anyway, yes. Recycling symbol number 3 for polyvinyl chloride. PVC is used for tubing, pipes, hoses. It's used also for toys. My most recent and continuing experience with PVC is sprinkler pipes. Some of you may be from the Midwest or New England, where sprinkling, water irrigation is something you simply don't have to do because God opens the windows of heaven and it rains. In the West and in the South, we sometimes have to water our lawns for them to survive. It's an open question as to why we should be having lawns anyway. But in any case, a lot of irrigation tubing is PVC. So a couple of interesting stories on PVC. Years ago, I bought a industrial. Oh, sorry. I'm really not getting emotional. This is not that kind of a story. Years ago, I bought a hose from Home Depot. It was advertised as industrial strength. I was excited because I was tired of having a hose that would kink, and then I'd have to go find the kink and unkink it. And so I bought this hose. And I had it for many years. I bought it in San Diego when I was doing my postdoc. I don't know why. We didn't have a lot of money, so I probably shouldn't have been buying hoses. But when we moved here, I hooked it up to our new house, and I was using the hose, and suddenly I was getting sprayed. Not by the end of the hose, but by a leak in the hose itself. Over time, the hose had started to crack, and there started to be holes in it. There's a reason for this, and the reason is that sometimes polymers, I've shown you that some polymers can be more rigid than others, for example, high-density polyethylene versus low-density polyethylene, and we've talked about how this has to do with how tightly the polymer chains can pack against each other. There are some polymers that pack tightly enough against each other that they are too rigid to be useful or to be involved in manufacturing. So what the engineers do is they add a molecule to the polymer, not covalently, but they just mix it into the preparation. The molecule's called a plasticizer to make it more plastic or malleable. The plasticizer gets in there and disrupts some of these non-covalent van der Waals forces that allow the polymer to pack tightly against itself. And that works. The problem is that over time, the plasticizer leaches out of the polymer and the polymer goes rigid again. So this is what happened to my hose that I bought that was industrial strength, is it sat outside, it was in the sun, the plasticizer leached out or was degraded, the polymer chains packed more tightly against each other, the polymer shrunk and started to crack, and then my hose was spraying me in the face. And not because a child was pointing it at me, but because there was a hole in the hose. Okay, so that's one story with PVC. Different preparations of PVC can vary in their resistance to mechanical stress. In Utah, where we need to irrigate, but we also have cold winters, PVC piping is a little bit problematic. So my first year here, my sprinkler system, I heard that you needed to, quote, blow out your sprinklers. Has anybody ever heard of that before? Yes? Yeah. So it's a good idea. The idea is that if your sprinkler's pipes are full of water, and then the water freezes, the water will expand, and the PVC polymer may or may not be flexible enough to accommodate the expansion of water. So I did what I was probably I was probably just barely turning 30 at the time, so I thought I knew everything. And I thought that can't be that important, so I didn't do it. And the next year when I went to start up the sprinklers, I was testing the various zones, and in my front yard, I mean, it was like, you know how, is it in Ezekiel or Revelation or both, where it says that waters will flow forth from the door of the temple and heal the Dead Sea and heal the whole earth? Well, like a whole section of my lawn had sort of lifted up near the driveway and water was pouring out from under it and going down. I had clearly done something wrong. So I turned off the water and ended up having to dig up a whole section of my lawn. I pulled out this really long pipe of PVC that had just shredded, like it had shredded in a spiral pattern. It had just, you could tell that the water got to a certain point and the pipe just went. And I've never done that again. I always blow out my sprinklers now to avoid that from happening. So again, polymer rigidity, flexibility is important for various properties. To this day, it's always an open question as to how, even if I blow out my sprinklers, there's always something that's a problem. Amber has learned, my wife Amber has learned, anyway, there's many things in my life of which I have to repent. I won't confess them all before you now, but getting angry at the sprinklers is certainly one of them. So, all right. Maybe just one or two more polymers. Okay, there's a chloro. What if we replaced all four of the carbons of ethylene with fluorine? This then becomes tetrafluoroethylene. And the polymer is polytetrafluoroethylene, or PTFE. Drawing this is going to be annoying, but because now all of the places, all of the carbons have two fluorines on them. So PTFE, or polytetrafluoroethylene, man, I'm wishing that I didn't draw the polymer quite so long. All of these carbons have two fluorines on them. It's as though the polymer is encased in a sheath of fluorine. How does that change the properties of the molecule? Well, fluorine is different from a lot of other atoms in the sense that it is the most electronegative of the elements. Electrons on fluorine are relatively low in energy. So it turns out fluorine doesn't really like to participate in a lot of intramolecular forces. Its electrons aren't high enough energy to be good nucleophiles or good donors. So fluorine doesn't do hydrogen bonding very well. It doesn't like to interact with water, but it also holds its electrons really tightly. And if you remember, these van der Waals interactions depend on the ability of a molecule to distort its electron density and polarize itself to interact with other nearby molecules. And fluorine doesn't do that kind of polarization very well. So fluorine's not that great interacting with water. Fluorine's also not that great in interacting with organic molecules. So somebody said this would be the perfect coating for perfect polymer coating for a surface that you don't want water to infiltrate, but you also don't want grease or oil to infiltrate. And thus was born Teflon. Okay, so a lot of us have cookware that's coated with Teflon. The reason it's coated with Teflon is won't let water stick to it and won't rust. So the Teflon protects the surface underneath from rusting, but it also doesn't, also oil doesn't stick to Teflon. So it's a decently good non-stick surface. Of course, mechanically you could remove the Teflon from the surface by scraping the pan enough. So all of us have probably eaten our fair share of of Teflon. Okay, speaking of polymers that we eat, we could do Elmer's glue, but I think that's probably enough to get started on. I guess the one other one, some of you are potentially interested in dental school, and so I'll show you a polymer that's used in dental composite. You're not going to like it, but you probably should know about it if you intend to. You probably should know a little bit about the chemistry of it if you intend to do dentistry someday. So, have you ever had a cavity filled? If you haven't, don't raise your hand. We don't want to know about your perfect teeth. But if you've ever had a cavity filled, after they do the drilling, congratulations, by the way, to all of you with no cavities. I congratulate you heartily. Yay. You're like, just brush your teeth more. I will, I promise. I'm trying. If you've ever had a cavity filled, there's a stage after they've done the drilling. They apply the dental composite, and then the dentist puts on yellow-colored glasses and sticks something in your mouth and pushes a button. There's a beep, and there's also a blue light. You ever seen that before? Yeah. So what the heck is he doing with the blue laser gun? He's polymerizing your dental composite. He's initiating the radical reaction that polymerizes your dental composite. So what I'm going to draw for you is more complicated than what I've shown you, but the polymer is going to have this same backbone of 2 carbon units alternating in a row, okay? So again, keep in mind what we've seen before for the monomer polyethylene and for polystyrene, polyvinyl chloride, this 2 carbon unit that has something attached to it. For dental composite, here is the 2 carbon unit. I'll highlight it in gray. That's what's going to be incorporated into the chain of the polymer. One of the carbons of the polymer has 2 things on it. One is a methyl group. The other is an ester. The other thing attached to that ester is this 3 carbon alcohol-derived molecule. It's derived from something called glycerol. And then this oxygen on the end of the 3 carbon unit is attached to a benzene ring. And then there's more. On the other side, it's just going to be the reflection of what we've already done. You don't need to memorize that structure. Unless I put it on the test, in which case you'll wish you had. Which of these molecules is used in dental composite? All right, see, you already know the question. You can recognize it. All right, so you have basically, this is what we call a bifunctional molecule. It's got 2 portions on it that can be involved in polymerization, and then it's got a linker between those 2. So this, now we're going to, as we polymerize, we're going to have a chain going in this direction and a chain going in this direction, and the linkages between those chains are going to be this portion, all right? I don't expect you to draw this, and we don't really have time for me to draw it, so I'm going to Frankenstein it together with some copy and paste action, okay? So here's one chain. This derives from those individual, this polymer would come from polymerization of this 2 carbon unit. Here's the methyl group, and then here's the linker, which I'm now going to copy and paste. Shrink. Oops. All right. And then this carbon over here is itself going to be linked Close enough to something like that. Okay? That's horrible, isn't it? And every other carbon, I'm just going to draw methyl groups. Oops. I'm going to draw methyl groups and R's. Every other carbon is going to have another one of those R linkers. And that R linker is going to be attached to another polymer chain. Perhaps this one. You know, there may be multiple times in which one polymer chain is linked to the other. Where two chains, oops, I didn't want it to be that close. Where two chains are linked really closely together. Sorry. There may be multiple cross-links between multiple chains, but basically at every point along this chain, you have the opportunity for one chain to be linked to another, forming a relatively rigid network of polymer molecules, which is exactly what you want if you want something that's attached to your tooth and not going to break anytime soon. The process of starting that polymerization required UV light. And the reason it required UV light was to get started what's called a radical reaction, which is what we're going to talk about now. But this is an example of the kind of thing that's involved in dental composite. Okay, anything you want to know about that? I got a couple more things to say about it that are just interesting. This thing is called BPA, glycidyl methacrylate, or it's called, or bis GMA. So if you're a dentist someday and you need to order some bis GMA, that's what you're ordering. Let's talk about what BPA stands for, because you've heard that term before. There's a lot of people advertising stuff to you today as being BPA free. So we want to just say a bit about what BPA stands for, because it's a common linker present in a lot of polymers, not necessarily the plastics we've talked about, but some others, which we won't talk about. But I do want to say something about BPA. That central unit, BPA, bisphenol A, is called bisphenol A. Two benzene rings with oxygens on them. A benzene ring with an alcohol on them is called a phenol. So this is bisphenol A, or BPA. Why would companies be advertising BPA, or rather plastics or various products as being BPA free? And the answer is that it's complicated, controversial, and not resolved. I'm going to draw for you the structure of a steroid hormone. Again, I realize that some of you are like, do I need to memorize that structure? No, you don't, but you need to make it look like you were in class today and were listening when I was talking. So here is the structure of estradiol, estrogen, okay? And you can see that it shares the phenol structure with bisphenol A. I don't care that you memorize the structure of estradiol, but if you relax your eyes a little bit, it shares some functional groups, right? It shares maybe the spacing of these two OH groups, more or less, and it shares the presence of at least a benzene ring. It turns out that bisphenol A can bind the estrogen receptor, though it binds the estrogen receptor, which I'm calling ER, the estrogen receptor, with 1,000 to 2,000-fold lower affinity. So it's certainly not as potent as estrogen at activating the estrogen receptor. Nevertheless, you can imagine that it might be bad to have large systemic exposure to bisphenol A if you want to. It might be bad to have large amounts of bisphenol A binding to your estrogen receptor and resulting in estrogen signaling in biology. Even at much lower affinity, that might have an effect. It's an open question, but you will hear people talking about plastics and disrupting endocrine signaling, and they're talking about the potential for bisphenol A to be involved in that. I'll let you, if you want, to do more reading on that subject. I don't know a lot about cell biology or plastics epidemiology. There are people who worry a lot about it. I just want you to think critically about the issues. You're going to have influencers tell you you should never microwave anything with plastic in it because it will disrupt your endocrine signaling. I don't actually know what the data are on that subject, but at least now you know the basis behind what they're saying, and it's sort of up to you to follow up and see what you can learn. Okay. Right. Anything else? Questions? Let's talk about radical reactions, how they're initiated, how they happen. Let me show you one such reaction for polyvinyl chloride. Got my notes all over the place. This is great. So, a radical reaction involves molecules with unpaired electrons. And radical reactions proceed in 3 different phases, only one of which is really important. Well, okay, I suppose they're all important, but the first phase is initiation. You have to generate the radical. And this means you're going to have to break a bond, and you need the breaking of the bond to be homolytic. That means each partner gets an electron. As an example, I show you a couple of molecules that can undergo homolytic bond breaking. If you use ultraviolet light and some molecules that have relatively weak bonds, you can break the bond. And this goes way back to the first lecture, the first 1 or 2 lectures in the class where we learned that a covalent bond consisted of 2 electrons shared in a bonding orbital, but that if you applied energy to promote the 1 electron to an anti-bonding orbital, you'd break the bond and each partner would move away. This is an example of that. You apply a photon of the right wavelength, and the bond between the bromines breaks, and you end up with 2 bromine radicals. Okay? Notice the use of the single flagged arrow. That indicates, normally when we've done reactions involving nucleophiles, we've used a 2 flagged arrow to show nucleophile attacks electrophile. The 2 flags, though you maybe didn't realize it, communicate movement of 2 electrons. If we just use 1 flag, we're talking about movement of 1 electron. We're going to be doing a lot of these 1 flagged arrows to show the formation and reactivity of radicals. Some other examples of molecules that have weak bonds between atoms that are good for radical initiation are peroxides. Here, R could be hydrogen or it could be something carbon. A good example that's sometimes used is tert-butyl tert-butyl peroxide. Here again, in some cases you don't need to apply light, you can just apply heat. And that's the organic chemical symbol for heat is the Greek letter delta. You apply heat and the bond breaks and you end up with 2 radicals. Radicals are molecules with a single unpaired electron. We'll talk about their reactivity. I want to show you just one more radical initiator. This one's a little bit more complicated. This one's called aza isobutyryl nitrile, or AIBN. And it's kind of fun because you don't have to memorize its name or its structure. The bonds that are going to break are these ones. The reason they're going to break is because this molecule comes spring-loaded with nitrogen gas that's just dying to get out of there. And if we apply a little bit of heat, what will happen is the bond between carbon and nitrogen will break. One electron will go to carbon. The same thing will happen on the other side. These two unpaired electrons will form the triple bond of nitrogen. You end up with two tert-butyl radicals and then nitrogen gas. This last of the three bonds between nitrogen comes from one of each electron from each of those original carbon-nitrogen bonds. Nitrogen gas, being a gas, bubbles out of your reaction mixture. Reaction is totally irreversible, and then you're off to the races. So your text will pretty much always just use light or heat, and often just use bromine as starting material. Sometimes we'll use peroxides. But there are a lot of ways to get radicals. I show you one that is actually used by a lot of organic chemists to begin with. So, in initiation step, you start out with something that is not a radical, no unpaired electrons, and then you go to something that is a radical where you have unpaired electrons. That's why we call it an initiation step. The second step, which is where most of the interesting chemistry happens, is called the propagation step. So in the propagation step, we take something that's a radical and we have the radical react with something else to generate a new radical. So I want to show you, since we've been talking about plastics, I want to show you how this works for polyvinyl chloride. Then we'll do some simpler small molecule reactions. Let's, for right now, just assume, I don't know what our radical initiator was, but I'm going to use the R for radical, okay? Radicals can react with a lot of other molecules in unique ways. We're going to talk about how to think about radicals and their reactivity. But for right now, let me just show you one propagation step. The single unpaired electron from the radical reacts with one of the two electrons of the pi bond to form a new sigma bond. Carbons, of that pi bond, we have carbons A and B. B is more substituted than A. We're going to talk about that in a little bit. Here is the new sigma bond that we formed. We form that regioselectively with carbon A so that the radical can be on carbon B. We started with a radical. After the reaction, we have another radical. That's a propagation step. All right, and unfortunately, that's all we have time for today. So we'll pick up with that discussion on Monday. In the meantime, you're bored this weekend, order some Shrinky Dinks from Amazon and have some fun.